Hello everyone and welcome to another episode of Interstigation. In today's episode of Interstigation, I will go over the Pythagorean Theorem. And I've already done a video on this, but I decided to do another one because this is one of the fundamental theorems in geometry and in coordinate geometry as well, and trigonometric as well. And this video I will try a new method using PowerPoints, and that will be more clean and concise. You will learn more in this video as well. So let's get started. In this video, the Pythagorean theorem only focuses on right triangles. So this acute triangle or any obtuse triangles does not count in Pythagorean theorems, and we cannot apply Pythagorean theorem on there either. So we only want the blue triangles or the right triangles in this case. And the Pythagorean theorem states that the lag squared, the sum of the lag squared is equal to the hypotenuse squared. And notice that this right angle is very important. And let's get into the history of Pythagorean theorem. Although the theorem has long been associated with the great mathematician philosopher Pythagoras from 570 to 500-ish BCE, it is actually far older, believe it or not. 4 Babylonian tablets from circa 1900 to 1600 BCE, which is like 1,000 years earlier than Pythagoras, indicate some knowledge of the theorem. A very accurate calculation of the square root of 2, which is around 1.41, and the square root of 2 is actually the hypotenuse of an isosceles right triangle with the lag length of 1. And the Pythagorean theorem is stated as: for any right triangle with a positive area, so it is not degenerate, we have the sum of the squares of its legs equal to the square of its hypotenuse. But why is the Pythagorean theorem true? Well, we're going to prove that right now. It's proof time. And in this theorem, we're actually going to prove it using one of the methods. And recall that if we have a right triangle with lag size a and b, then we have a squared plus b squared is equal to c squared. That is true for all right triangles, not necessarily all triangles, but all right triangles. And let's try to prove that. Since the expression consists of squares, we need to try to somehow get squares involved, and squares, their area is just the side length squared. So if we somehow get square involved and use the area, somehow we can try to prove that. Let's say if we draw a square with side length a plus b, then divide it up somehow. So if we have this side length a plus b, divide it up like this, so like this, then each side would be a, and these sides would be b, 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 and b. And if we connect that, each hypotenuse, if we connect that, we figured that each of these triangles are congruent because they're all right triangles with side length a and b. So we have all right triangles, they're congruent, so their hypotenuse is equal to c over here. These are all c's. And the big square, we can calculate the area of that. That's just simply equal to a plus b squared. Alright? The a plus b squared. And there are the other way to represent the area, and that is the 4 triangles added together add the central square. So that would be equal to, 4 times 1/2 AB, that plus the central square, that is c squared, what we have. Because the central is definitely a square, since this angle and this angle add up. So this angle, since they're congruent, this angle is equivalent to this angle, and these two angles add up to 90 degrees. So this definitely has to be 90 degrees as well. So that, if we simplify that, we get a squared. If we try to simplify that, we get a squared plus 2ab plus b squared is equal to 2ab plus c squared. If we cancel out ab, then we would get a squared plus b squared is equal to c squared, which is exactly what the Pythagorean theorem says. And that's the proof of Pythagorean theorem. Now we've went over the proof of Pythagorean theorems, we can go over some common Pythagorean triples that we might use later. And the most common one is definitely 3, 4, 5. That is 3 squared, 9 plus 16 is equal to 25. And a less common one, but still common, it's 5, 12, 13, which is 25 plus 144 is equal to 169. And 7, 24, 25 is also another Pythagorean triple. But what if you want more triples than just these three and the multiple of these three? For example, 3, 4, 5, we can have 6, 8, and 10 as well. Well, that is easy. If we have A, B, C as side lengths of a right triangle with A is less than B is less than C, then we have C is definitely the hypotenuse, right? So we have A squared plus B squared is equal to C squared by the Pythagorean theorem. If we rearrange it a little bit, we get A squared is equal to C squared minus B squared, which is equal to C plus B times C minus B if we use the difference of squares. Then we would get that for any pair of integers BC, I mean, it doesn't have to be integers, but it works the best with integers because we're most familiar with integers. You can generate an integer A such that A, B, C form a right triangle as long as A plus B is greater than C. And that is the triangle inequality. We have the extension of Pythagorean theorem. Pythagorean theorem is actually a special case of law of cosine that states for any triangle, not just right triangles, it can be acute, it can be obtuse, that c squared is equal to a squared plus b squared minus 2ab cosine c. And we have cosine 90 degrees is equal to 0, so that the last term disappears in Pythagorean theorem. That just becomes c squared is equal to a squared plus b squared. Also, this is a visualization of this, that this a, b, and c, it fits this identity, and this requires a little bit of trigonometry, but it is far more, I guess, utilized than Pythagorean theorem, and the law of cosine is actually very important in later math. Also, you can switch the sides of these three triangles of the triangle so that the AVC switches and this identity still meets, which means that c squared is still equal to a squared plus b squared minus this, although the cosine value is the angle opposite to it, which means it would change as well, and the equality still meets. We also have 367 known proofs of the Pythagorean theorem. So that's what I just went through is just one of them, one of the many Pythagorean proofs. Also, the distance formula is derived from the Pythagorean theorem as well. It states that the distance between 2 points on the coordinate plane is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. And if we see a visualization of this, you see that it's basically the Pythagorean theorem with the x length of x2 minus x1 and the y length of y2 minus y1. Thank you for watching this episode of Investigation, and I will see you in the next one. Goodbye.